In this video, I am going to talk about how to write differential equations for problems involving air resistance. So first off the bat, a differential equation, as we can see here, is an equation that involves a variable and one or more of its derivatives. So how do we get an equation that could possibly do that? So let's take a look at an example. I'm going to have an object that falls to the ground that experiences some air resistance, and we're going to say this air resistance is proportional to the velocity. So if you were to drop this from rest, the first second or two it's not going very fast, so the air resistance is relatively small because the velocity is small. But as it speeds up, as it goes to the ground, the air resistance gets larger and larger. Um, so this is the free body diagram for that situation. And so I'm going to write the force equation that goes along with that. I'm going to write the y equation. If I sum the forces in the y direction, I get BV minus mg, my template here, equals m a j equals something. So that's your force equation. Typically we solve for velocity, or we'd use kinematics to solve for this acceleration to find the velocity. However, this acceleration is not constant. It's changing all the time because the velocity is changing and the overall force is changing, and so it's not linear. So in order to solve these problems, we need to use differential calculus. So this is where the differential equation comes in. To get a differential equation, you need a variable and its derivative. So right now I see no derivatives. However, if I take a look at here, I have velocity and acceleration. And I do know that acceleration is dv dt. So to get a differential equation, I can say bv minus mg equals m dv dt. And so by taking the a out and replacing it with dv dt, I have an equation with a variable v and its derivative, its first derivative. In later problems, we are going to learn how to solve for the velocity as a function of time, and then graph it and all that good stuff. But you can kind of see we have velocity and time. A little bit we have its derivative. But in later problems, we'll solve for this equation using u subs, separation of variables, and things like that, things you learn in a calculus class. Here's another example. What if the object's air resistance doesn't depend on its velocity, but depends on its position, minus b, let's say y, meaning as it goes to different elevations, its y changes because of the air density or humidity or things like that. The air resistance changes. What if we have that situation? Well, it's very similar. I'm going to sum the forces in the y direction like we did before, and I have, this is actually a plus, not sure why I put a minus there. It's going to be by minus mg equals m a j equals 0. And it is accelerating. Should have crossed that out over here. So we can cross that out. So how do we get a differential equation here? Well, here there was a direct relationship between velocity and acceleration, but we also have the same thing here. We have velocity is dx dt, and we have that acceleration is dv dt. So another way stated, we can say acceleration is the second derivative. I probably should use y here for displacement, but it's the second derivative of the displacement. So I can rewrite this as by minus mg equals m d squared y dt. I switch back to y here for this particular equation. So here's an equation with a variable and its second derivative, another differential equation. And again, using techniques in calculus, you could solve for an equation of y as a function of time. For this particular problem, all that's being asked is to write a differential equation. So basically it starts off with a force model, and then we can use these relationships here that we know from calculus to arrive at a differential equation. And we can also use this technique for rotational motion. So likewise, alpha is equal to d omega dt, and alpha is d squared theta dt. So we can use this for the rotational model as well.